Web developers have a distinct advantage when analyzing an application. They open Chrome DevTools, inspect the DOM, and immediately see the exact state of every element. The DOM is the Document Object Model, a programming interface that represents a web page as a transparent, structured tree. Desktop binaries offer none of this visibility. Desktop frameworks like Java Swing or WPF operate as FAT clients. A FAT client is an application that runs as a standalone native process directly on the user's machine. Its state, which tabs are open, what text is typed, which nodes are expanded, lives entirely in local memory, completely hidden from external tools. Without a DOM or external inspection APIs, automated tools are forced to interact with the UI through brittle pixel scraping and screen-based coordinates. This opacity contributes to a significant discovery gap during modernization. Teams often spend months building a replacement based on the source code, only to find that the live application behaves differently than the static files suggest. If you cannot natively observe the running application, AI agents and human engineers are building based on assumptions. They are forced to guess at user workflows and logic paths that only exist in active memory. In a legacy FAT client, the definitive source of truth is not a database schema. It is not a requirements document. It is the live process memory. Desktop UI behavior is inherently nonlinear. The application state reacts constantly to unpredictable external triggers, mouse clicks, focus changes, background timers, and data arrival events. Over decades of active use, complex behavior emerges organically. One developer adds a listener to update a status bar. Another adds a polling timer to the same component. The resulting interaction creates a workflow that users depend on, but which appears nowhere in the original specifications. Standard accessibility APIs exist to read some of this state, but they were designed to stream limited data to screen readers. They lack the structural depth and serialization speed required for comprehensive analysis by an AI agent. To accurately map these systems, we have to bypass external observation entirely. We have to embed an HTTP server directly inside the application process to report its state from the inside out. Converting the opaque binary into a self-reporting system provides the exact operational logic an LLM needs to understand the interface. The Java Swing MCP project is a lightweight library built to solve this exact problem. It gives AI agents structured, semantic access to Java Swing applications. This diagram shows the architectural insertion point. A single method call initializes an HTTP server inside the JVM on port 9222, the isolated runtime engine executing the compiled application code. Operating inside the environment eliminates the need for complex bytecode instrumentation, remote debugging tools, or fragile JVM agent flags. External wrappers have to guess at the interface state. This embedded server has native, unrestricted access to the live AWT component hierarchy. AWT is the Abstract Window Toolkit, Java's underlying platform-dependent windowing API that holds the actual structural map of the UI. An external Python orchestrator can now query this embedded endpoint via standard HTTP requests. It retrieves the exact component states, text fields, combo boxes, table rows, exactly as the application itself sees them. The desktop application is no longer a closed black box. It operates as a transparent, queryable API. Legacy Java UI frameworks operate under a strict threading constraint, known as the Event Dispatch Thread, or EDT. The EDT is a single, dedicated background thread responsible for processing all user interface events and visual updates. The system enforces a hard invariant. All component reads, writes, and interactions must happen exclusively on this single thread. This creates an immediate architectural conflict. The embedded HTTP server receives incoming external queries from the AI agent on a completely separate thread pool. To resolve this, the server relies on the invoke and wait bridge pattern. The HTTP thread pathway halts, safely passes the execution request over to the EDT pathway, and waits for the EDT to return a completed result back across the bridge. This execution must be synchronous. The HTTP handler is actively blocked until the exact updated UI state is returned, ensuring the external agent receives accurate data before its next move. Blocking the thread guarantees absolute safety. An external AI can puppet a legacy UI in real time, executing clicks and reading tables without causing memory race conditions or crashing the application. Delivering the UI state to an LLM introduces a context window problem. AI agents struggle to parse and navigate the raw, deeply nested data trees typical of desktop applications. Standard JSON indentation creates deeply nested layers that waste thousands of tokens on formatting alone. The architectural solution flattens the tree into a one-dimensional array. Instead of nesting, each isolated object holds a direct parent ID pointer that explicitly maps its relationship. To maintain structure, the system uses a stabilization protocol. It assigns persistent, non-recycling integer IDs to every UI component, storing them natively in the application's memory properties. Stable IDs allow the LLM to deterministically reference specific components across multiple sequential API calls, even as the interface changes. The server then applies specific noise reduction layers. It drops non-semantic layout containers, like invisible JPanels, saving context space without removing meaningful data. It applies an interactable filter. The API isolates and delivers only the components the user can actively use, like text fields and buttons, further reducing the payload size. Flattening the structure and filtering the components translates a sprawling desktop UI into a dense LLM-optimized data structure that preserves complete semantic relationships. Even with an optimized UI tree, orchestrating multi-step AI agent workflows creates memory bloat. A complex debugging session can quickly hit 50,000 tokens. The context window is rapidly exhausted by two specific data types: massive table data extracts and the base 64 PNG screenshots, captured after every UI action. To prevent the agent from failing midway through a task, the Python orchestrator implements a sliding window token compaction mechanism. The orchestrator estimates total token load before every API call. When the count hits 80,000 tokens, a compaction filter sweeps the oldest data in the session history. It strips raw image bytes, leaving text placeholders, and summarizes dense table grids into brief text descriptions. By aggressively compacting historical evidence but preserving recent action results, the orchestrator allows an AI to maintain its chain of reasoning through complex, multi-step interactions without exceeding model limits. Exposing the application's memory to an HTTP port provides capabilities that extend far beyond AI agent operation. It gives human modernization and QA teams precise, programmatic access to the system. Because the server can query every UI component, it enables programmatic WCAG contrast auditing across the entire legacy application. WCAG is the Web Content Accessibility Guidelines, the international standard for defining digital accessibility thresholds. The server algorithm traverses a component's parent chain to calculate its effective background color, returning an actionable list of specific elements that fail strict accessibility compliance. The library also includes a user action recorder. By attaching a global event listener to the live UI, it tracks the organic, undocumented workflows of real human operators. It translates a user's organic clicks and keystrokes directly into time-stamped markdown logs. Crucially, it outputs executable curl commands, turning a manual session into a fully automated replay script. Observing the application from the inside transforms subjective, manual quality assurance into precise, automated, and mathematically verifiable test suites. A legacy FAT client is no longer a static, unreadable artifact to be feared during a rewrite. The static source code is not the documentation. The live process memory is the documentation. Enterprise architects can now systematically explore and map 20-year-old software systems using the exact same standard REST APIs they use for modern web services. This yields a system where AI agents can successfully execute complex enterprise workflows and navigate deep UI logic entirely autonomously. Embedding an MCP server bridges the gap between legacy enterprise systems and modern LLMs. It allows organizations to move from guessing at legacy behavior to building against a documented, observable truth.